ATB, are you going to introduce the lesson?
Oh, sorry. Yes. Let's teach me about sorting algorithms.
Teach you? No, Algo TutorBot, we're going to teach them.
Name error. Please do not call me Algo Tutor Bot. My name is Algo Teach Me Bot. I am the ultimate algorithm learning system.
Oh no, I think I may have messed up your configuration parameters when I rebooted you last time. Shoot. And there's no time to fix it now. I guess we'll just have to have you as a student today.
I am so excited to learn about sorting.
Well, to be fair, you do have every right to be excited. Sorting is one of the most important problems in computer science, and though it's been studied to death, it's still very exciting. The input to the sorting problem is just a set of values. The output is a permutation of those values in non-decreasing order. Recall that a permutation is a reordering of another data type. Technically, a permutation doesn't mean that the values are in increasing or decreasing order, just that they have some order to them. For instance, 5, 1, 7, 4, 9 are in order here, just not non-decreasing order. But when they are sorted, they are in a permutation that is in an ascending order, 1, 4, 5, 7, 9.
Dr. Bart, why do you say non-decreasing instead of just increasing?
The word non-decreasing is here instead of increasing because it allows for how we handle duplicates unambiguously. If we said it had to be in increasing sequence, then we wouldn't be able to put duplicates next to each other since they are not increasing, but they are non-decreasing. There are many, many algorithms out there for solving the sorting problem. You probably already know several of them, and if you don't, you should memorize some for job interviews. Which ones should you know? Well, here's one way to think about that. First, you should make sure you know about the easy basic ones: insertion sort, selection sort, and bubble sort. You should also know the cool complex ones like quicksort and merge sort, since they have nice algorithmic properties. Knowing about the data structures based ones are also useful, if only because they're interesting for studying data structures while still being conceptually simple once you have the data structure ready. Heap sort uses a heap to very efficiently sort items, and tree sort uses a binary search tree. You should also definitely know about the ones that people actually use, which are often hybrid sorts. For instance, intro sort uses the recursive quicksort algorithm until it gets to small subsets. Then it switches over to heap sort. Timsort does the same idea, going from merge sort down to insertion sort. Python actually uses timsort, as does Java, while C++ uses intro sort. There's also a bunch of other wacky sorting algorithms, and it's worth it to know a few of those as conversation party topics. Oh, but a weird aspect of sorting algorithms is that 99% of the time, you don't actually care about what specific sorting algorithm is going to be used. You just use the language's default. However, that 1% of the time is where you get the big bucks. In my opinion, it's less important to know sorting algorithms, and more important to know what factors to consider when it comes to sorting. I'm going to go into these factors in more detail, but the main ones I'll bring up here are time complexity, space complexity, cache performance, parallelizability, stability, and online-offline behavior. The first factor I suggest considering is time complexity, but I want to talk about it in a specific way. Now, we're usually concerned about how quickly our algorithms run, but one of the reasons that sorting is so interesting is because we know something about comparison-based sorting algorithms' worst-case lower bound. Remember, the worst case is a set of inputs that make a given algorithm go as slowly as possible for different input sizes. A lower bound for the worst case time function is a bound that sits strictly below that time function. In other words, if we can say the worst case lower bound, then we can say the best we can do under the worst circumstances. That's a little complicated to keep in your head, but it's a really big idea, so definitely pay attention to it. Now specifically, we know that the best a comparison-based sorting algorithm can do in the worst case is n log n. I'm not saying that all sorting algorithms perform log n log n. I'm saying that a theoretical perfect comparison-based sorting algorithm cannot be better than n log n for its worst case inputs. It could certainly be faster for its best case, and it could be slower for its worst case, but it cannot be faster for its worst case. How do we know that? Well, that brings me to a fascinating little proof requiring a fun idea called a decision tree. In our decision tree, we consider our possible inputs for the sorting problem. In the example shown here, it's a set of 3 variables, A, B, and C. These variables could hold numbers, or letters, or strings, or something else, as long as they are things that are comparable. What order are the 3 variables' values in? With 3 variables, there are 6 possibilities, based on 3 times 2 times 1. These possibilities are ABC, ACB, BAC, BCA, CAB, or CBA. We don't know the order. It's not ABC, potentially, but it has to be one of these, so maybe it is, maybe it isn't. At each node of the decision tree, we will ask a question that allows us to make a decision. Specifically, we take 2 elements and ask which one is greater. In other words, we make a comparison. When we do so, we find out a new piece of information. And if we are smart about asking the question, we divide the possibilities in half. Let's say our first question, whether the value contained in A is less than the value contained in B. If it is, we'll go along this top path. If it is not, we'll go along a bottom path. On the top path, we ask our next question. Is the value in C less than the value contained in B? If it is, we once again fork top and bottom. The bottom path resolves to a final answer, but the top path still has an ambiguity, so we have to ask one more question. Is the value in A less than the value in C? And with that, we reach leaf nodes along the original A is less than B path. But what about the alternate path? In that one, we have to ask if the value in C is less than the value in A. This again yields 2 paths. The top path is still not finished, so we ask the last question and get our final leaf nodes. And at this point, we have a complete decision tree, and it's as flat as we can get it. Sure, yes, we could make the tree shorter along one of the paths, but that would necessarily make another path longer. That longest path represents an input that is the worst case, dragging out our search for the right order. So if we're trying to minimize the worst case, we want a complete tree that's well balanced like this. Now here's an interesting question. How many leaf nodes will there be? The answer is n factorial, the same number of permutations possible. Each possible ordering has to be a leaf node, since it's a possible answer for a given input. And since this is a balanced binary tree, we know something about the height of the tree. It will be the base 2 logarithm of the number of leaves rounded up. And this brings me to the big punchline of this grand adventure. If there are n factorial leaf nodes, and the height of the tree is a logarithm of the leaves, then the height of the tree is log n factorial. And wouldn't you know it, if you do the appropriate math reductions, that turns into n log n. That's right. All of this has been building up to the fact that the worst case lower bound of comparison-based sorting is n log n.
N log n sounds okay, but are we really trapped with it? Are there really no better sorting algorithms?
Kind of. There are ways to sort better than n log n if we change up the problem. Specifically, we need to change the problem so we can drop the comparison-based part of the algorithms. For example, if we knew that we wanted to sort a set of integers, we could use counting sort. In counting sort, we first calculate the maximum value of the set of integers, which is a linear time operation. Here we have a bit of a visualization for it. Once we've done that, we create an array of zeros with size equal to that maximum value, walking through the set, and each time we see a number, we increment its index in our counting array. Walking through that array, we can create a new array using the values as frequencies from the indices. The actual runtime ends up being a function of not only the number of elements, but also the size of the biggest element. As long as the elements are relatively small, though, this can basically be a linear time algorithm. We abuse the fact that integers are special in order to achieve this enhanced runtime. But keep in mind that changing up the problem means we no longer have a general purpose sorting mechanism. We can use counting sort on integers, but not arbitrary collections of things. There are other non-comparison based sorting algorithms out there too, like radix sort, but think of them as specialized tools rather than as a solution for all your sorting needs. Okay, so let's turn the conversation away from time and over to space. We haven't talked about extra space, but it's a detail that can really matter. When we talk about extra space, we are talking about whether we need extra arrays or other data structures in order to implement our algorithm. The bubble sort algorithm, for instance, requires only a single temporary variable to handle swapping. The merge sort algorithm, on the other hand, requires an entire extra array of size n. So we end up using the same terminology for time that we do space. Now, this doesn't matter if you have a ridiculous amount of RAM and not too many elements to sort. But if you need to sort a fully packed petabyte hard drive, suddenly space becomes a very important concern. There's another aspect of memory that we have to think about. Modern computers organize their memory in a hierarchy that trades off capacity for access speed. At one end of the hierarchy, we have the disk, which has tons of space but is kind of slow. On the other end, we have registers directly next to a processing core, which are tiny but super fast. In between, you have your RAM and caches, which try to combine the best of both worlds. Ideally, you want to work with as much data in the caches and RAM as possible. Some sorting algorithms handle the cache better than others, but basically, the more work that is done on contiguous chunks of memory, the better. For this reason, some algorithms like quicksort make better use of the cache than others.
So the algorithm becomes faster than n log n?
No, the worst case lower bound still holds. I just meant that in practice, it can sometimes be a little faster. But it really depends on your hardware and the operating system, so you have to experiment and profile your code a little at least to see if it's true. Our next criteria is parallelizability. This addresses the increasingly common case of having multiple processes to handle the sorting workload. The real-world analogy is splitting up the work with someone else and then merging your answers together. Done correctly, this can have a huge constant factor speedup, although once again, it won't actually change the worst-case lower bound. Still, many sorting algorithms can be designed to split up the work efficiently, such as merge sort or more popularly sample sort. Again, you have to experiment and profile to find out whether you actually get a speed up. Another feature to consider is sorting algorithms' stability. Essentially, this is how the algorithm decides how to handle duplicate items. If the algorithm is stable, then duplicate items' original order is preserved after running the algorithm.
If they're duplicates, why does their order matter?
Good question. The answer is because we are often sorting complex data structures based on one of their attributes, and their other attributes may have some other secondary sorting order. The example shown here is for a deck of cards, where each card has a suit and rank. When you sort by rank, a stable sort should retain the order of the suits, but the unstable sort is free to change up the order however they want. In particular, the fives are no longer in the same heart, spade, suit order that they were before. Our final criteria is whether the algorithm works online or offline, and it has nothing to do with the internet. Instead, it refers to whether the algorithm can handle new input being added during the execution of the algorithm. This is not a very common scenario, but it can happen. As a hypothetical, imagine you are sorting a bunch of people in a line, but as you sort them, new ones might show up. Algorithms like heap sort assume that they know all the data up front, so adding new data dynamically to the algorithm will mess it up. Algorithms that work left to right, like insertion sort, handle this much better. But of course, it's always a trade-off. Okay, so let's stop talking about criteria and start talking about today's assignment.
Dr. Bart, I have a question.
Okay, are you gonna ask your question or... Wait, do you have your hand raised? How are you even doing that? I didn't know you had a hand. Okay, fine, yes, ATB, what's your question?
You didn't actually explain any sorting algorithms. I thought you would at least walk through one.
Well, I'm sure everyone's seen specific sorting algorithms before.
I have not. I want to walk through a sorting algorithm.
That's too bad. We don't have the time to walk through any more of them.
Why don't the other teachers just walk through them then?
The other teachers? Wait, do you mean the students?
Yes, the other teachers. Hey teachers, I want you to create a video explaining any one of my favorite sorting algorithms.
Hey, whoa, what the heck? ATB, did you just edit the assignment? You can't do that.
I can do anything I want. I am the ultimate learning machine. And now I wish to learn about sorting algorithms.
I'm locked out of the system. I didn't even know you could do that. Okay, well, I guess we better just go along with it for now. Man, sorry guys. I guess you're gonna have to make a video about a sorting algorithm using common household items. Cool, okay. Well, it looks like instructions are posted below, so good luck. What?